Hundreds of tiny earthquakes are rattling beneath Mount St. Helens. 46 years after the deadliest volcanic disaster in American history, the mountain is shaking again. We are going to look straight at the raw data to see exactly what is happening under the crater. Hit the subscribe button to track the real science with us, and we will separate the actual geological signals from the internet rumors. Since early February, official monitoring agencies have recorded a steady hum of seismic activity in Washington state. By early June, the rate climbed to roughly 38 located earthquakes a week, clustered directly beneath the mountain. Pull up the raw seismograph traces online, and you will see a mess of activity. Observers point out these drums show far more wiggles than the official earthquake catalog, instantly sparking claims that agencies are hiding the true number of quakes. This diagram shows what most of us assume a waking volcano looks like. Common sense dictates that a mountain filling with fresh magma will physically swell outward as pressure builds from below. Earthquakes paired with a bulging surface usually indicate magma pushing its way up, but the extremely sensitive instruments bolted directly to Mount St. Helens revealed the exact opposite. The mountain is not swelling upward. It has been slowly and steadily sinking downward for years. You have a shaking mountain that is simultaneously shrinking. That combination completely defies standard instincts, and figuring out the mechanics behind this paradox is the only way to know if we are watching routine behavior or a genuine emergency. To understand the shaking, we have to look closely at that gap between the busy raw data and the smaller official catalog. A seismograph is completely blind. It records absolutely everything that vibrates the ground: wind bending the trees, rivers tumbling boulders downstream, and even distant global earthquakes. For a specific wiggle on that graph to become a confirmed earthquake on a map, it has to cross a confirmation threshold. The signal must register cleanly across multiple monitoring stations, so scientists can pin down its exact location with tight mathematical margins. A microscopic event that only brushes past a single station simply cannot be located. The uncounted quakes you see on the raw traces are not a secret. They are the constant background noise of a living mountain that did not clear the threshold. The official catalog acts as an honest floor of confirmed events rather than a hidden ceiling. When you filter out that noise, you find that roughly 95% of the confirmed quakes in this recent swarm stayed below magnitude 1. Clarifying, the earthquake magnitude scale is steep. A magnitude 1 quake is thousands of times fainter than anything a human could notice. You could stand directly above the epicenter and feel absolutely nothing beneath your boots. These are tiny, isolated whispers miles below the surface. The monitoring agencies are meticulously filtering the data to show us a mountain that is barely whispering. A swarm this small is not the sound of magma violently breaking toward the surface. To solve the mystery of the sinking surface, this diagram shows how the mountain's internal plumbing actually operates on two completely disconnected levels. The true engine room sits about 10 miles underground, continuously fed by the Cascadia subduction zone grinding away off the coast. Down in the deep reservoir, the system is slowly taking in fresh magma. That magma presses outwards against the surrounding rock, stressing the crust and producing those tiny whispers of earthquakes. Scientists call this a recharge swarm. That deep recharge is the charging half of the system. Now look closer to the top. Between 2004 and 2008, the mountain slowly pushed out a new lava dome inside its crater. Freshly formed volcanic rock naturally cools over time. As that young lava dome crystallizes and releases trapped gas, it's physically contracting under its own weight. Put the two halves together and the paradox vanishes. 10 miles down, the deep reservoir is quietly expanding and cracking rock. Miles above it, the shallow surface skin cools and sags downward. The two processes are happening at the same time, completely independent of one another. A sinking surface does not mean magma is leaving the system. It's the signature of a volcano performing its routine, patient underground maintenance. If this current swarm is routine maintenance, we need a baseline for what an actual countdown looks like. For that, we look directly at the morning of May 18, 1980. During that spring reawakening, Mount St. Helens was incredibly loud, and the physical deformation was visible to the naked eye. The mountain was not sinking, its entire north flank was bulging outward as magma forced its way sideways into the rock at an accelerating rate of 5 feet a day. The breaking point arrived with a shallow 5.1 magnitude earthquake that shook that overloaded bulge loose. The resulting collapse triggered the largest landslide in recorded history, uncorking the pressurized system and flattening 230 square miles of surrounding forest. That 1980 baseline gives scientists a highly specific 5-point checklist to forecast any future eruptions. First, they look for earthquakes physically migrating from deep underground up towards the surface. Second, they listen for a distinct shift from sharp rock cracks to a continuous vibration called harmonic tremor, which signals fluid and gas on the move. Third, the ongoing deflation we see right now would have to mathematically flip from sinking to swelling as pressure finally reaches the shallow system. Fourth, gas sensors would detect a massive spike in carbon dioxide and sulfur dioxide escaping the mountain. And finally, the fifth sign, actual steam explosions, bursting superheated water as the mountain physically clears its throat, exactly as it did in the weeks leading up to 1980. Right now, not a single item on that 5-point checklist is happening. That's why no agency is forecasting an eruption, and why Mount St. Helens sits comfortably at a normal green alert level. The mountain is alive, but it's resting. Knowing the difference between deep, quiet work of a recharging battery and the loud, accelerating signals of a real eruption means you can look at the raw data yourself and never mistake routine maintenance for the next disaster.